graphical representation of Arrhenius equation. We already got an expression log k is equal to log a minus a by r into 1 by t. And this I have rearranged in the format log k is equal to minus a by r into 1 by t plus log a. And this is of the format y equal to mx plus c. Y equal to mx plus c is the general form of a straight line graph. So here instead of y you have log k and instead of x you have 1 by t. So we'll plot a graph log k versus 1 by t, and this is a straight line with a negative slope because the slope is equal to minus a by r. So this is the graphical representation of the Arrhenius equation, and by calculating the slope we can determine the value of A, that is activation energy. Now here we will discuss the integrated Arrhenius equation. We have the expression of the form log K1. Here I given K1 because we consider the temperature as T1. Whatever it may be, it is a general form T1. At a T1 temperature, the rate constant is K1. So the expression becomes log K1. Here 10 indicates the logarithm is based on the 10. That's why it is log 10. You need not to be bothered about that. So we can say log K1 is equal to log A minus A by 2.303 R T1. Similarly, at another temperature T2, we'll consider the rate constant as K2. So we get expression log K2 is equal to log A minus A by 2.303 R T2. So these are given as equation number 2 and equation number 3. And subtracting the equation 2 from 3, we get log K2 minus log K1 is equal to A by 2.303 R into 1 by T1 minus 1 by T2. This is of the form log A minus log B. Log A minus log B is log A by B. So it is log K2 by K1 is equal to A divided by 2.303 into R into 1 by T1 minus 1 by T2, which upon rearranging you will get log K2 by K1 is equal to A by 2.303 into R into T2 minus T1 divided by T1 into T2. This expression is known as integrated form of Arrhenius equation. With this expression, we can calculate the activation energy by knowing the rate constant K2 and K1 at two different temperatures called T2 and T1. Let us try to calculate the activation energy. We have a problem here. The rate constant for a first order reaction is 1.6 into 10 raised to minus 5 second inverse at 600 Kelvin and 6.4 into 10 raised to minus 3 second inverse at 700 Kelvin. Calculate its activation energy. So we have two different rate constants at two different temperature called 600 Kelvin and 700 Kelvin. Since you have two different temperatures and two different rate constant, we can make use of the Arrhenius integrated expression log K2 by K1 is equal to EA divided by 2.303 R into T2 minus T1 divided by T1 into T2, where K1 is given as 1.6 into 10 raised to minus 5, K2 is given 6.4 into 10 raised to minus 3 second inverse, T1 as 600 Kelvin and T2 as 700 Kelvin. We'll substitute all these values in the above expression, so it takes the form like this: log 6.4 into 10 raised to minus 3 divided by 1.6 into 10 raised to minus 5 is equal to EA into EA divided by 2.303 into the value of R is 8.314 joule per Kelvin per mole into T2 is 700 minus T1 is 600 divided by T2 into T1, that is 700 into 600. Now, upon solving this value, we will get log of 4 into 10 raised to minus 2, which is equal to the same value as above. Now, this is of the form log A into B raised to n. Log A into B raised to n. That takes log A plus, instead of n, you have 2 here, 2 log 10. Log 4 plus 2 log 10, which is equal to the same above value. Now log 4 is 0.6, log 4 is 0.6, log 10 is 1, so 2 log 10 becomes 2, log 4 is 0.6, so it is 2.6. So the value of log 4 into 10 raised to minus 2 is 2.6, which is equal to the above expression, the above value. Now we get EA is equal to, by cross multiplying this value, it becomes 2.6 into 2.303 into 8.314 joule per Kelvin per mole into 400 Kelvin. That is the value by solving this one, and which is equal to, here you have 209086.79 joule per mole, which is converted into kilojoule as 209.09 kilojoule per mole. That is the value of activation energy. So that's all about the Arrhenius expression. We discussed the Arrhenius expression, and it's a representation, logarithmic, then the graphical representation, then the integrated expression, and based on that we done a problem to calculate the activation energy.